thanks very much, John. Thanks for the introduction. Thanks to the organisers for the invitation. And yeah, right. So apologies for the sort of glib title, but honestly, for us, this has just been an ongoing saga, and so we were just so relieved that this is really okay. It really does seem to be a noise-free system. So I'll tell you about it. So this is all work that's been done at the IEP, at the Clarendon Lab in Oxford. That's pretty much the only nice picture I could find of it with nice weather. And this is all work that's been going on. So the director of these labs is Ian Walmsley. And so you'll know that a lot of the stuff going on there is work on integrated photonics, heralded photon sources, waveguide circuits. We have a collaboration with Sewu, who's here. Hi, Sewu. On these fantastic superconducting detectors. And obviously everyone in Bristol will know about the promise for this kind of stuff. Just a quick note is so I'll be moving in about a week or two to the CPPM at Bath. So Pete Mosley, who's also here, Pete, is the director there. And I'll be setting up a new group looking at, so again, light storage and vapor, like you'll be hearing about today, a bit of diamond optomechanics, hopefully should be fun. Some stuff on Rydbergs, well, let's see. And so, anyone who's interested to join, please do let people know that students and postdocs are much appreciated. Okay, so why this quantum photonics malarkey? Everybody has their own reasons for doing it. Obviously, you can send photons over distance. You can do standoff sensing and detection. It's really the only quantum platform you can stick down fibers and think about making a long-range communications system. So for my money, a really key thing is that photonics is fast, right? So the carrier frequency of optical photons is around 100 terahertz, and that's why in classical telecoms we can already use photonics to carry gigahertz and even hundreds of gigahertz bandwidths of data. And this will carry over into quantum information processing as well. And really the key thing for me also, there's this final, maybe slightly naughty picture, right? Which is just looking at the effective temperature for different quantum platforms, and photonics is really the only one that sort of natively runs in ambient conditions. So I'm looking at superconducting qubits or ND centers, trapped ions, phosphor donors, spin qubits, quantum dots. All these things need to be cold. Now, you can put them in a fridge, or you can trap them, stick them in a high vacuum and optically cool them. But really, it's only photons that you can imagine really just living quite happily with no thermal noise in quantum states of room temperature. I think this is the most exciting aspect. Okay, and you'll know that we can also put photonics into the solid state by writing waveguides, and here's some nice pictures. These are from Southampton. This is femtosecond writing from Oxford. And then in the medium term, there's this idea that you could already achieve interesting devices just by using photon sources, these integrated photonic circuits and photon detection to do boson sampling type problems. And is boson sampling useful? Well, there's even a cool proposal from Alan Asbury-Guzik that by just realizing that vibronic spectra in molecules are essentially coupled harmonic oscillators, and that the transport of photons through a waveguide chip is also a set of coupled harmonic oscillators. You can make predictions about useful chemical predictions about the vibronic spectra of molecules that are computationally hard to simulate using this kind of idea. Okay, great. But in the long term, we know that what we really love is to grow enormous entangled states, which will be a resource for quantum computing on an arbitrary scale. And this cool donut is from Simon Benjamin, because I guess the surface code has the topology of a torus. It just also looks really cool. And so we have a problem, which is, okay, in Star Wars we can get photons to bounce off each other, but otherwise photons don't interact. So how are we going to make a computer? Of course, in Ephraim's group, they do interact, and there are various tricks to try to make this happen. but in general, the idea of linear optical computing is to kind of fake it. What do I mean? So here's an example of a nonlinear sign shift gate where we use an ancilla photon that is combined on a beam splitter with some other number of photons. Now, if we detect a photon on the other side, well, it could have been the ancilla that bounced off, or it could have been one of these guys from this mode. And there's an interference between those two possibilities. And because it's a beam splitter, transmission and reflection have a different sign. So the weighting of those two interference terms is weighted by the number of possibilities for the transmission, which is the number of photons. And so I can end up with either a positive or a negative sign for this state, depending on the number of photons. Okay, great. The only reason I just run through that is basically the only one I can understand. There are lots more ideas for this. But the key thing is this just has a tiny success probability of a few percent. Here's a more advanced one that you might like to try, which is trying to make a GXZ state. And this is a tripartite entangled state that you need if you're going to grow cluster states. And so here's a little interferometric scheme for how you might do it. These green things are deterministic photon sources, and then you plug them together into this little interferometer, and if you get 3 clicks, one on each of these pairs of detectors, you make a GXZ state with a probability of 1 on 32. And so, this is a basic primitive of photonic quantum information processing. It's been around for a while. You might think it's been done, but it hasn't. It's too hard. And there's a nice paper from Simon Benjamin and also Peter, who I think is also here, might be here, who looked into the resource costs for this kind of thing if you just add more and more redundancy to try to deal with this probabilistic nature, and it scales pretty horribly. So we need some kind of multiplexing. Spatial multiplexing is the idea that you just put lots of copies of your device. Spectral multiplexing is where you can use the frequency degree of freedom to essentially try many operations in parallel, different color each time, and when one of them works, you shift the frequency. And this is a neat paper from Wolfgang Tittel over in Calgary. Temporal multiplexing, this is something that came out of the group here in Bristol, I think it was last year. And it's this idea that you want to switch photons in time. And so that's really the motivation behind this talk, is that if we have quantum memories, we can do this temporal multiplexing. We can store the results of a successful operation until all the other contingent operations have succeeded, and then we can release them on demand. So how do we store light? Clearly, what we want to do is have a little fiber switch and just switch the light into a loop and just go round and round and round, and then when we need it, we switch it out again. I mean, why would you do anything else? Right? This is obviously the way to go. I don't have a good answer for why this doesn't work. It should work. So you guys, please solve this problem. Right now, a lithium niobate modulator has 50% loss. That's useless. That's terrible. You can't. I mean, you go around like twice. So turns out this seems to be a hard problem. If you can fix it, you've solved quantum photonics. You've built a quantum computer. You're done. Okay, and so there's progress being made in this. This is kind of the best you can do with bulk optics. It's a very nice experiment. It still turns out it's hard. So the other approach is to think about storing light in a stationary excitation in some atoms. Okay, so that's what I'm going to talk about. And for a long time, we've pursued this protocol, the Raman memory protocol. We like it because it's a broadband. It allows us to select the mode that we store and shape it. And also it runs at room temperature, which again is consistent with the major advantage of photonics, right? Put it in a fridge, well, why not pick a superconducting system? Okay, the way Raman absorption works is we optically prepare a bunch of lambda-type atoms in one of their ground states, and we always use cesium, the hyperfine ground manifold. And the photon we want to store comes along off-resonantly, and then when we want to store it, we send in a strong control pulse that satisfies 2-photon resonance, and that just stimulates anti-Stokes absorption on this. Actually, it's actually Stokes absorption in this diagram. And then this now survives as a sort of stationary excitation for a little while, and then when we retrieve it, we send in the control pulse again, and we get our photon out again. And so this is not in chronological order, but this is an experiment we did with this protocol where we allowed the atoms to diffuse into the core of a hollow fibre, which is a large core Grommet fibre that we got from Philip Russell's group. And this was the experiment. We had 2 vacuum chambers, and the cesium diffused from an ampule into the core. It took about 6 months, a bit annoying. Anyhow, we were able to show that we could do optical pumping in that system to prepare the atoms. And then, as the number of atoms in the fibre core increases, and we blast them off the wall using atomic desorption with a laser beam, then you can see more and more of this input pulse is absorbed, and you can see a little bit of retrieval here. And as we increase the number of atoms, you can see the absorption gets stronger, and the retrieval also gets stronger. So this is storage and retrieval of sub-nanosecond pulses in this Raman type memory. But if we look closely, so this red trace, this is the retrieval, so this is storage and retrieval at a single photon level. And if we look closely, this red trace is photons that are retrieved from the memory even if we block the input. So even if we don't send anything in, we get a few photons out. Okay, there's about a 10% chance of getting a noise photon out. And so we also had an experiment with a bulk system. This was just a vapor cell with this, so no atomic desorption needed because we didn't have this fiber anymore. And this is a little experiment showing again storage and retrieval. These are weak coherent states, as was the previous experiment. And again, this red trace is the noise that's coming out at the single photon level. This purple trace is the difference between them, so don't worry about that. Okay, and then we also did an experiment with a heralded single photon source. So we had a periodically poled KTP waveguide chip, which we pumped with doubled light from the TISAF. And then when we get a detection of an idler photon, then we're able to switch this signal photon into the memory and store it. And these are the data for the arrival times, and so it really looks identical or very, very similar to the coherent states. That's good. I mean, the memory works the same for single photons as it does for coherent states. But okay, this noise is still here. Okay, maybe perhaps you wouldn't expect anything else. And so we wanted to look at the statistics of that noise. We did 3 experiments. This is looking at the light transmitted straight through the memory. This is looking at the light retrieved from the memory. And this is looking at the light transmitted through when we just don't bother to prepare the atoms and we switch off the optical coupled. And so these are some measurements of the autocorrelation function, the G2. It's a Hanbury-Brown twist measurement where we look to see, do we have 2 photons after in these fields or not, right? And so the classical bound for this G2 that indicates Poissonian statistics is 1 here. And we start off with a very small G2 coming from the photon source, about 0.02. And after we send the photons through the memory, you can see already that G2 is up at about 0.9, right? So just by going through the memory, we're still non-classical, but only just sub-Poissonian. And then here you can see these are the results being retrieved from the memory. The green is coherent states, about 1.7. And okay, there's a little drop. It gets a little bit closer to 0, right? 1.6 for single photons. Okay, but ultimately, let's not beat around the bush, right? So this device is an almost perfect converter of single photons into thermal states. Right? So thermal light would have a G2 of 2. Actually, only single mode thermal light has a G2 of 2. So this is quite hard to achieve, right? If you do a Hanbury-Brown twist on a candle, you get 1 because it's multi-mode. So this is a pretty clever thermal light source. Anyway. If you imagine the noise is coming from uncorrelated noise, from some uncorrelated process, then you can convolve the 2 distributions, the noise distribution and the single photon distribution, and predict the G2 you should get, and it doesn't fit. So this is not a kind of uncorrelated noise process that's coming out of the system. And so this is what's going on, and many of you would have seen me talk about this before. What you have is the control pulse can couple to the ground state. In this system, we don't have a selection rule that prevents that. And in that case, I can get a spontaneous anti-Stokes scattering that's going to produce a spurious excitation in this coherence. And that can now be retrieved as a noise photon. So the reason it calls 4-wave mixing is because there are 1, 2, 3, 4 waves involved in that process. And now if you do the theory for this, then okay, it fits. So we understand what's going on. This is the dominant noise process in this memory. How could we suppress it? Well, one thing is to try to introduce a selection rule so the control field has nowhere to go when it couples to the ground state. Very annoyingly, it turns out that this type of alkali atoms are kind of like a Mach Zehnder, right? So there are two hyperfine states up here, and there are two routes to get between these two hyperfine states. You can go via this guy on the right or this guy on the left, and they have precisely opposite phases, and so the probability for this cancels. So you can't do that. You could try to rely on phase matching. If the refractive index is significantly different for the Stokes and the anti-Stokes, then this four-wave mixing process doesn't conserve momentum properly. Unfortunately, the phase mismatch is not so big in cesium because this ground state splitting is just 9 gigahertz. So it's not as bad a problem as it would be if the splitting was 0, but it's also not big enough to suppress what we're doing. Okay. Another method for noise suppression that we looked into was putting a cavity around the system and trying to arrange that the cavity was resonant for the signal field that we want to store, but anti-resonant for this spurious anti-Stokes scattering that initiates the noise process. And remember, we only need it to be anti-resonant in the direction that we're going to retrieve from eventually, right? Because everything else is not phase mapped. And okay, there's a subtlety that we also have to get the control field in, whose frequency is right in the middle of these. So we have to make a birefringent cavity. Anyway. So how much suppression can we get from this system? Essentially, it's something you can directly measure. The noise suppression is just or another way of saying is that the signal-to-noise ratio you expect is going to be the maximum of the density of states divided by the minimum of the density of states here, which is just exactly what you get if you measure the cavity transmission function and take the ratio. And again, the G2 you expect is going to go inversely with that. There are some advantages with the cavity, right? These cavities are always tempting for quantum optics people. You're like, well, first, if I put a cavity in, I get an enhancement in the effective number of atoms because I pass through the atoms many times, so I get a factor of the finesse in the effective optical depth. And I also get an enhancement of the intracavity field. So if I resonantly couple my control field, I have effectively a much stronger control field and I can run this on lower power. Okay. Unfortunately, every time I go around the cavity, I lose a little bit because cavities are never perfect. And in fact, so the best efficiency I can get is limited by the round trip losses. And so this is something that there's an engineering challenge to really push down the round trip losses. This is a demonstrator that we built, and you can see we were able to get these triple resonance conditions: anti-resonance, resonance, and resonance in the other polarization for the control field. So these are the guys who built it. Dylan is also here, over there, and had to be locked and stabilized. It was a bit of a tricky experiment. This was when we first saw memory, and I came in and took a photo, and the retrieval is right there. Okay, so we got the data off the scope, and this was able to. We still have a little bit of a noise trace, but suppressed by about a factor of 3. So we were happy with this. And this shows the efficiency fits the theory. It's limited by round trip losses. So okay, I finally come to the point. Why are we storing in spin states? So the protocols that are based on storing in long-lived spin states are really based on the original motivation for quantum memories in terms of quantum repeaters. And that's where the latency is set by the travel time between two sites in a communications network. And that can be quite long. Maybe you need milliseconds of storage time. On the other hand, for the application I just outlined, where we really want to synchronize entanglement generation or single photon sources, this is a local application, right? Everything's sitting in the same lab, and so the latency can be low. It really depends on the clock rate that you can run your system at. And as I said, since the carrier frequency of photons is hundreds of terahertz, we can run an optical system at a very high clock rate. It could be a gigahertz, it could even be 10 gigahertz. And so how long is long enough? It's a few hundred clock cycles at a gigahertz, I think. So maybe a few tens of clock cycles. Something like 50 or 100 nanoseconds is about what you need. So let me just run through again some of the disadvantages of the Raman protocol that I've been talking about. One of them is that to prepare the storage state, I need to optically pump the system into one of the hyperfine states. And it turns out that when the density gets very high, this is a little bit challenging, right? You get light trapping in very dense vapors where fluorescence actually unpumps atoms you've already pumped. And here's a nice result from a paper from our student Sarah Thomas and Dylan, who led the work, just showing that actually you can extend the temperature that you can do this optical pumping out much higher if you use the right buffer gas. But nonetheless, you can see these guys fall off a cliff edge at some point with temperature. So another thing is that the bandwidth you can store is limited by the splitting of this ground state, because you don't want these two fields to overlap in frequency. This splitting is 9 gigahertz, so that really limits this memory to about a gigahertz bandwidth. Another issue is collisional fluorescence, which has been seen in a lot of these lambda type memories. I'm sorry, this is a terrible thing that I did on the train, so it's almost impossible to understand what I'm trying to indicate. But when a buffer gas atom collides with one of the alkali atoms, during the collision you get a really rapid evolution of the phase as the energy levels are distorted by the collision. And this has a timescale on the order of picoseconds, which means the bandwidth of this process, of this line width, can be hundreds of gigahertz. And that means even if you're far detuned in the Raman limit, you can still see collisional fluorescence. And here's some data from one of our Raman memories. Actually, it doesn't really affect us in our memory because we time gate. This is 30 nanoseconds, and our pulses are half a nanosecond. But not everyone can do this, and this has been an issue for lambda type systems. Also, filtering is tricky. These two fields are co-propagating in the Raman memory, and they're separated by 9 gigahertz with about a gigahertz bandwidth. Right? So, I showed this diagram from the cavity memory before. This right here, that's 7 epsilons. That's 7. I mean, there's no end to the hell that's been in aligning and tuning those epsilons into resonance and trying to reduce the losses of that filtering system. Okay, and of course I've talked a lot about forward mixing as an issue in these systems as well. So let me introduce then this new protocol, which is a fairly simple evolution of what I've just talked about, but I think it comes with a lot of advantages. We tried to think of an acronym. After about an hour that we will never get back, we came up with ORCA. Anyway, there were some much ruder pictures for the other acronyms, so this is good. Basically, the idea is to stop thinking about a lambda type system where we're storing in spin states for quantum repeaters, and say, what about if we store in a doubly excited orbital state? What if we turn this into a lab system? Now, this is not going to have milliseconds lifetime, but it might have hundreds of nanoseconds lifetime, long enough for this synchronization. What advantages accrue if we do that? Well, there's no optical pumping needed at all, right? So the population of this state is 0, or at least it's 10 to the minus 17 or something ridiculous at room temperature, right? So this is KT, which is much larger than the hyperfine splitting, which is why you need optical pumping. But it's hugely smaller than this splitting. Also, there's no bandwidth limitation from the splitting. So before we had to limit our bandwidth. In this case, of course, there's no limitation here. The bandwidth can be the splitting between these two states is twice the carrier frequency. Okay. Also, the wavelength difference between the signal and control can be much bigger than hundreds of gigahertz. So there's no need to worry about collisional fluorescence. And actually, in fact, you don't really want a buffer gas anyway, because your storage time isn't going to be on the order of milliseconds, and buffer gas may not be very friendly with orbital states. Also, if we have a large frequency difference, there are no echelons or cavity filters needed to separate this. We can separate the fields with interference filters, single pass filters, interference filters. And also, note here, there's a counter-propagating configuration here, and so the fields are even traveling in opposite directions. Finally, there's no equivalent of forward mixing noise. So again, this was done on the train. I'm sorry about this laborious diagram. What I'm trying to show is that in this type of alkali system, what we're doing is storing this guy up into the orbital state, and the equivalent of a forward mixing process is when the control field couples down to the ground state. So I'm waiting for my slow diagram to get there. If the control field couples to the ground state, you can see it can scatter spontaneously into the other hyperfine state, which was the source of the noise previously, but it can't produce an excitation upstairs. Right? And that's because there is such a thing as spontaneous emission in quantum mechanics, but there's no such thing as spontaneous absorption. Right? I can't spontaneously absorb a photon from the vacuum. And so there's no equivalent noise process to forward mixing. This is a demo that we just done at Oxford. We used cesium vapor. Again, we were sort of set up to use cesium. We're using the D2 line at 852 nanometers for the signal, and this transition up here from the P state to the D state at 917 nanometers for the control. The setup is essentially quite simple. We just have a cesium cell and the control and the signal coming from opposite sides. We were lucky that we have two TISAFs. Thank you to the UK Quantum QTech program and the enormous rush on spending that ensued for that started. So, these were some of our first results where we stored classical light. We just stored pulses from the laser. So this is a log scale here. This is showing the amount of light that we retrieve, and so you can see the efficiency is just switching on and then topping out here. But this was the noise level we were measuring, which is completely flat, and this was limited by dark counts of our detectors. So you can see storage and then retrieval. And then we wanted obviously to look at the statistics for storing single photons. And so again, we used our periodically polled KTP waveguide down conversion source, which is here. Now we could use it in a degenerate configuration, and so both the signal and the idler pass through a filter to filter them down to about 1 gigahertz to match the bandwidth of the laser. And then we herald on an idle click, and the heralded single photons pass into this guy. Because this memory doesn't need any optical pumping, and it has actually a pretty short lifetime for this demo, we could run this whole experiment at 80 megahertz, and that allowed us to collect pretty good statistics. And this here is a Hamby-Brown twist measurement. This trace is showing the arrival time, so again you're seeing storage and retrieval, and this is happening at 80 megahertz. And then here, this is looking at coincidences between the idler detector and one of these two signal detectors here. And so this is again showing storage and retrieval. This is actually a subsequent retrieval pulse, but on this side, you can see nothing, right? And this here is the accidentals. So this is where you don't expect there to be a coincidence. And this coincidence to accidentals ratio is about 150. And then the final measurement we wanted to do was to look again at the autocorrelation. So are we making thermal states again? 2 minutes? Good, okay. Again, the G2 of the photons we're producing by the source is about 0.02 now, so we're able to get a pretty well anti-bunch source coming out. And this diagram shows you the ratio of triples events to in orange to coincidence events, which is okay. And so you can see this blue trace is it's just the doubles, and the orange down here is the triples. So this is for the light coming into the memory, and now. The big reveal is let's take a look at what comes out of the memory, and again we have a similar plot, and you can see really the triples are way down, and the G2 is the same. So within error it's also 0.02, 0.03 maybe. This really is a noise-free memory, right? We're not able to see any added noise on our photons from storage and retrieval in the system. All of the noise processes that were there in Grommet are now absent. There's no fluorescence noise, there's no forward mixing noise, there's no thermal noise, there's no control field leakage. There's really, all of those confounding factors are gone in the system. So this is exciting for us. We've been working on it for a while. The paper's out, it's on the archive. The storage time is short in the system. It was 5 nanoseconds. And that's from Doppler dephasing because the atoms are moving around like bilio. The next step then would be to go to a system with where these two fields are much closer to degeneracy. And so an obvious example is to go to rubidium vapor, where these transitions are very close in wavelength. And in that case, the counterpropagating configuration makes you almost Doppler-free, and you expect a lifetime of around 50 nanoseconds, which will be long enough for this synchronization. So we're excited to give that a go. Many thanks to all the people that worked on this. So in particular, you should note Dylan's contribution, also Chris, who is the lead on this, as well as Patrick Ledingham and Benny Brecht, who worked also on the ladder storage. Thanks very much.
Questions? Questions back from Chris?
I missed, you might not have said it, the retrieval efficiency is the retrieval efficiency is still looking good. I mean, it's reasonable. What is the number of that efficiency and what prospects for scaling it better?
Okay, good point. Yeah. So in this experiment, the retrieval efficiency was about 15%, and then through the various filtering, we lost about another factor of a third. So the end-to-end efficiency was about 6%. But like I say, we're excited by the system because you don't have these cavity filters. You don't need them. It doesn't seem obvious that there's a reason why you couldn't really push that up towards in the 90s and the high 90s. The limitation for the efficiency here is to do with just like the Raman interaction. There are some, if you're able to shape your pulses a little bit, your control pulse, then you can optimize the efficiency, and the asymptote for that is 1. Right? So we didn't do any pulse shaping, and that's why it was limited.
Again, one question from the chair there. The full wave mixing situation, you can configure it so that you can generate pairs from 1 photon in. In this situation, can you go from 1 photon to 2 photon forces? So you can get heralded pairs.
It's an interesting point. I mean, these type of ladder systems are interesting because of the other things you can do. So there is, I mean, it's a Chi-3 system. There is full wave mixing in the system. You can make kind of a diamond configuration where you generate pairs of photons. That's not a process that adds noise to the memory, but you could think about using it as a source, which you could then directly interface with the memory. So I think that'd be quite fun to look into.
Okay. So let's thank Josh again. You can ask more at lunch.